Okay, so as stated in the annotations, there's practice problems available. You can take a look at those. They're PDF available on my website. There's like a direct link I can post in the chat. That's a direct link to the PDF of practice problems. And of course, I'm also baking an apple pie, so that'll be happening at the same time. But if you have any questions about calculus, happy to answer them. Try to keep an eye on the chat so I can answer questions you type, or feel free to use the mic, ask questions by voice, anything. Great, thanks. Step one for me right now is making some instant coffee. So. So yeah, as stated in the email, happy to answer homework questions, questions from previous worksheets, from discussion sections, this week's worksheet, practice tests, anything. Sure, yeah. So a visual intuition for the three fundamental theorems is the question. And I guess the fundamental theorems we're referring to here are Green's theorem, Stokes' theorem, and the divergence theorem. And I think I'll even throw in a fourth one, which is the fundamental theorem of calculus, which turns out to be yet another one of those same fundamental theorems. In the end, it turns out if you take a fancy differential geometry class, you'll learn how to combine all of these theorems into one like mega powerful theorem that works in any number of dimensions. But for us, we have these like four separate ideas. Fundamental theorem of calculus, that's like our one-dimensional version. Green's theorem, that's our two-dimensional version. Stokes' theorem, that's like our three-dimensional version, and divergence theorem is also our three-dimensional version. Anyway, so let's just review what those are as equations, and then we'll talk about the visual intuition. And then there's another question about the sign of the normal vector whirlpool for figuring out the boundary orientation. So we'll talk about that too. Let's do that after this. But yeah, so first of all, our fundamental theorems. I think I'll remove one of these annotations if I can here. That one's gone. Okay, I'll just try to leave that corner of the screen unused. Actually, I have a question first. If I take this text annotation on the side here and I drag it off of my iPad screen, can you see it? Probably not. I have to guess. So let me instead try to give that a solid background if possible. Not sure how to do it. Okay, let me make that different somehow. Well, okay, there's a link to the practice problems in the chat, and I'll just let people know if they can't find them later. We'll just use that. Okay, so hopefully you can see me drawing these integrals here. Fundamental theorem of calculus is like the the easiest version of all these fundamental theorems. And it says this: if I integrate the derivative from a to b, I just have to take the original function, evaluate at b, evaluate at a, and subtract the answers. So this is what we use all the time to actually compute definite integrals. And then we have Green's theorem in 2 dimensions, which says that the integral over some region D of the z component of the curl of a vector field is equal to the integral over the boundary of D of the circulation of the vector field. So this is fundamental theorem of calculus, Green's theorem. And then graduating from Green's theorem up into surfaces in 3 dimensions, we have Stokes' theorem, which says, oof, terrible, okay. All right, Stokes' theorem says that the integral over a surface of the curl of a vector field is equal to circulation of the vector field on the boundary. So this one looks very similar to Green's theorem. It is very similar to Green's theorem. In fact, Green's theorem is just a special case of Stokes' theorem in the situation where the surface S we're considering, it lies on a plane. So we'll talk about that when we do the geometric intuition. And then our final fundamental theorem before is the divergence theorem, which says that the integral, the flux of some vector field through a surface is equal to the integral over the interior. Actually, let me rewrite this so it's consistent with the way I've been writing the other ones. Really should say the integral over a 3D region E of the divergence of the vector field is equal to the integral over the boundary of the flux. Okay, so this is the divergence theorem. All right, so those are our 4 fundamental theorems, and let's talk about the geometric intuition for all of these. So I guess the first one, the fundamental theorem of calculus, I don't want to spend too much time on, and because we already know that one. The basic idea is just that if I want to figure out what was the total change in the value of a function from point A to point B, I just add up the instantaneous rates of change all the way between A and B. So that's on the left-hand side, I'm integrating from A to B the instantaneous rates of change, and that'll tell me in total how much total change did I experience on the function f from A to B. And the second one, Green's theorem, is really a new theorem to us. So we have, in this situation, let's look at this setup. We have some region D, which might be, like I drew it, like simply connected, or might not be simply connected. Maybe it has some holes in it like this. So those are 2 perfectly good examples of what D could be. And what Green's theorem says is that if I want to know the circulation of some vector field around the boundary of a region, all I need to do is integrate the curl over the interior. So and the geometric intuition here is that, so let's think about this first picture here. If I have a vector field, I can imagine that as kind of like describing the way some fluid is flowing. So maybe I imagine this region I drew, this region D, as like a lake. I have like the boundary of the lake, and inside there's the water. And the vector field is describing how is the water moving through the lake. The circulation of the vector field is like how much is the water flowing along the side of the lake. Instead of like pushing out into the boundary of the lake, how much is it flowing along the lake? That's the circulation. And the curl inside is measuring at each little point inside the lake. The curl is measuring how swirly is the water's motion there. So you can imagine at some points in the lake, you'll have like little vortices, very swirly. At some points in the lake, the water's all going to be moving the same direction, just a smooth flow with no curl. And so that's what our curl is measuring. And the statement of Green's theorem is that to figure out the total amount of swirl around the outside, I integrate all the little curls on the inside. Maybe like an example of this would be if you're sitting in a perfectly still lake, there's no curl at all inside, all the water is not moving at all. That's describing the situation where the vector field is always zero. There's no motion of water. And then I'm in the very middle of the lake, and I take a little spoon and I dip it into the water, and I just spin it around a little bit, just a little spin at the center of the lake. What I've done by just swirling a little bit of water at the center of the lake is I've introduced some curl into the vector field at that point. Now the water there is moving, the vector field is non-zero, and moreover, because I was swirling it, it has some curl. And because I'm spinning the spoon at the center of the lake, you can imagine, even though it'll be very slow, that motion of the water at the center of the lake will eventually translate to the outside. And like the water molecules at the very edge of the lake will also be moving very slowly in the same direction that I spun at the center of the lake. So pictorially, I like have the vector field being zero, and then I introduce a little tiny bit of curl at the center. And what this forces to happen is that the whole lake itself starts rotating very slowly around. Very, very slowly, because I just added a little bit of motion to the lake. But that little tiny amount of curl that I added, if I integrate over the entire inside, tells me that the circulation is going to be non-zero around the outside. That's what Green's theorem is telling me, is that any little bit of swirl inside contributes to motion on the outside. Okay, and that would also be true in this kind of situation with this poorly drawn boundary. Let me try that again. Okay, something like that. We have some region here which is not simply connected. So there are these holes inside that aren't in the lake. Maybe these are like islands in our lake. In this situation, the water can swirl, the water can kind of swirl around these islands in a way that might not have been possible before. Because it doesn't need to smoothly continue inside the region of the island. But in any case, Green's theorem tells me that if I want to figure out the total amount of circulation in this case, I need to count not just the circulation around this like outside boundary of the lake. I also need to think about the circulation around the islands, because that's really the boundary of the lake. In this case, it consists of three separate parts. It has this like big curve on the outside, and then it has these two smaller curves on the inside. So the total circulation in this case is the sum of those three line integrals. And when we do these line integrals, we have to be careful about our orientations. So in the previous example, we have to be careful about our orientations as well. The important thing is to use either the right-hand rule for these little whirlpools, I think the way it was done in lecture, or you can imagine the way to orient the boundary of your region is to imagine yourself walking along the boundary of your region while keeping the region itself to your left. So in the case of this simply connected region D here, if I start at some point on the boundary and I want to keep the lake to my left, I need to move this way along the boundary. Moving the other way would put the lake on my right. Because I'm imagining that the lake is below me, I'm standing upright on the boundary of the lake, so I have to move this way. Okay, so that forces the boundary of the lake to be oriented like this if I want to apply Green's theorem. And in this example, the outside boundary is oriented the same way. But these inside boundaries are a little different because at the inside of the boundary, like here on this island, if I want to keep the lake to my left, I have to go around clockwise the little island inside. That has to be the orientation of that curve. And the orientation of the outside curve still has to be counterclockwise to keep the lake on the left. When you're doing Green's theorem, you just have to be careful about which way you orient the boundaries. And that's true for all of these theorems, Green's and Stokes and divergence theorem. Also true for the fundamental theorem of calculus in the sense that if I integrated from b to a instead, I would not get f of v minus f of a, I'd have a negative answer. That's true for our line integrals and our surface integrals as well. If we choose the other orientation, the answer becomes negative of what it was. Okay, so that was long, but that's Green's theorem. Let me know if you have any questions about that so far. Now I'll move on to Stokes' theorem. So Stokes' theorem is basically Green's theorem, but our surfaces are allowed to exist in three-dimensional space. In Green's theorem, the region we're talking about is a surface. It just happens to live inside this plane, like the xy plane. And in Stokes' theorem, we're allowed to have any surface at all. It doesn't have to live in the xy plane. So we can imagine a situation in Stokes' theorem that's like, we can imagine a similar situation to Green's theorem, where this coordinate axis here. If I imagine that I draw my region from Stokes' theorem, from Green's theorem in the xy plane in 3D space here, let's imagine this is y, this is x, and this is z. Then we can say, okay, some region in the, imagine I'm drawing this region in the xy plane. So this region here. And in the case where my region in Stokes' theorem, where my surface in Stokes' theorem is entirely contained in a plane, the theorem is exactly the same as Green's theorem. Because in that situation, the normal vector to this surface, if I choose it to be oriented upward, let's say, the normal vector would always be 0, 0, 1. I just wanted to point straight up. My surface is perfectly flat in the xy plane. And so in that situation, when I go to actually apply Stokes' theorem, I use this equation here. And I notice that my vector ds, like this vector differential, is going to be just pointed straight up. And at the same time, so this vector differential here is going to be 0, 0, 1 times ds, the differential surface area. And the curl here will then be dotted with 0, 0, 1. Dotting with 0, 0, 1 just gives me the z component of the vector, because the x component gets multiplied by 0, the y component gets multiplied by 0, the z component gets multiplied by 1, and I add up all those answers. So this curl of f dot 0, 0, 1, that's just going to be the z component of the curl times the differential surface area. And because this is totally flat, I can use my differential surface area to just be dA, and that reduces exactly down to Green's theorem. The statement of Green's theorem is that if I take the z component of the curl dA, I get this like same integral on the boundary here. Those are the same. So Stokes' theorem is just a generalized version of this, where if I were to choose my surface to be totally flat, I get exactly the same thing as Green's theorem. I'm just computing the integral of the z component of the curl over the surface. And if my surface is not totally flat, the good news is I can still apply Stokes' theorem. Even though Green's theorem no longer applies, I'm in 3D space. Stokes' theorem lets me do stuff with any kind of surface in 3D space, as long as it's bounded. So we need like our surface to not just stretch on forever in all directions. But I could imagine choosing, instead of a flat plane, I could be doing Stokes' theorem to a different surface, like a hemisphere or something like that. And in that scenario, Stokes' theorem is really saying the same thing, except it's a little harder to interpret geometrically. It's telling us that the circulation on the boundary of the surface is equal to the integral of the curl. And by the integral of the curl here, I really mean the flux of the curl, because the curl is a vector field, and that integral we're taking is the flux integral. So we're saying that the flux of the curl is equal to the circulation of the vector field around the boundary. And this really is saying the same thing as the geometric picture of Green's theorem. It's saying that the circulation around the boundary is the sum of all these little contributions on the inside of how much swirliness we have at each point. And if you add up all those little tiny bits of swirl, you get the total amount of circulation on the outside. So in this scenario, I guess kind of what we're saying is to find the total amount of circulation around the boundary of the surface, what we need to do is add up at each point how much the vector field is swirling like this. And because the vector field is in 3D space, it might be swirling in like many different directions. It might not be swirling in like on the surface of the sphere. It might be swirling kind of orthogonally to that. And so that's why we have to take kind of the flux of the swirl. The flux of the curl is telling us how much is the vector field curling along the surface, on the surface, instead of like in other direction. So by adding up the total amount that the vector field is swirling on the surface, we get the total circulation around the outside. So that's Stokes' theorem, just a more general version of Green's theorem, really, that allows us to use any kind of curved surface with a boundary instead of like a region in the plane. Okay, and then there's the divergence theorem, which is the next step up. We're going from, instead of in the fundamental theorem of calculus, we integrate over line segments. In Green's theorem, we integrate over regions. In Stokes' theorem, we integrate over surfaces. Those are two-dimensional. In the divergence theorem, we can integrate over a three-dimensional region. And the idea for the divergence theorem is pretty nice, but I'll draw it in 2D because I don't think I can do it very well in 3D. And there is a 2D version of the divergence theorem, but we just haven't learned it. So the idea for the divergence theorem is if I'm trying to compute the flux of a vector field on the boundary of a region, what that's asking about is I have a vector field and I want to know how much is the vector field moving through the boundary, not like parallel to the boundary, that would be some kind of circulation. How much is the vector field going through the boundary? So if we're imagining like if we're imagining a surface as like kind of a sail or something, and the vector field is describing wind, then the flux of the vector field would be telling us how much wind is the sail catching. How much is the wind going into the sail instead of like along the sail? That doesn't help us move. But into the sail, that helps us move. That provides some rest. So, and I guess this is a more general concept because we don't have to have like a sail. It could be any kind of boundary of a region in 3D. So the divergence theorem says that if I'm looking at the boundary of a region in 3D space, and I'm taking the flux of a vector field, how much is the vector field going through the boundary of the region? I can figure out this quantity by integrating over the inside the divergence. And what that means is, or like the geometric picture here, is that if at some point on the inside the divergence is positive, the divergence is measuring how much stuff is being created or destroyed at each point. So you could have a vector field like this, and if this were describing water, this seems kind of physically impossible for water, right? Because there's no way water could just be spreading out from one point. By conservation of matter, there'd have to be water coming in somewhere. But vector fields don't care. So the divergence of a vector field tells us like how much stuff is being created or destroyed at each point. If I have a point like this where all the vectors are pointing out, that's positive divergence because we're just like producing water springing out from this point in all directions. And if I have a point like this is like sucking in water. That has negative divergence because it's basically destroying water. It's not sending it anywhere else, it's just going to that point and being destroyed. And if we add up in total how much water is going through the boundary, this has to be the integral of the divergence because you can imagine kind of if this was the only point that had any non-zero divergence, if that had positive divergence and every other point had like zero divergence, what that would mean is at this point we're creating some water, and everywhere else where there's zero divergence, water isn't being created or destroyed. So it's not like the water's being like totally preserved. And because we're creating water at the center and it's not being destroyed anywhere else, it has to eventually flow out the outside. So that's the idea of divergence, is it measures how much water is being created at each point. If I have some points with negative divergence and some points with positive divergence, maybe water is being created someplace and then sucked in another place. Like maybe there's like a faucet that's dropping water into a pool and then a drain that's sucking the water out of the pool. But if the divergence is positive in some places and it's never negative, so it's always like positive or zero, that means we're just like pouring water into this pool at different places, and eventually that water has to flow out the outside of the pool. If we're just throwing more and more water into this region, it has to go somewhere. And so that's what the flux is measuring. The flux measures how much water is passing through the boundary, and that has to be the total amount of water that's being added to the pool. So that's the concept of the divergence theorem right there. All right. Any questions about those? All right, so I had another question, which was, how do we determine the sign of the normal vector for the little whirlpools? Okay, so the normal vector itself doesn't actually have a sign. A vector, it has a magnitude and it has a direction, but it can't be like, it's not like positive or negative. What you can do is you can take a vector and you can negate it. For every vector, there's a vector that has the same exact magnitude and points in the exact opposite direction. So you can take a vector and take its negative, that's a real thing. But it's, even though you can take a vector and take its negative, there's no such thing as a positive vector or a negative vector. They can be negative, they can be like opposites of each other, but neither one is positive or negative. And when we're orienting surfaces or orienting curves or orienting regions, any of those things, we always have two choices. So if it's like a sphere, we can orient with the normal vectors pointing outwards or the normal vectors pointing inwards, and those are both perfectly good choices for orienting a sphere. And in each of these theorems, like the Green's theorem, Stokes' theorem, the divergence theorem, we have to first choose an orientation on the higher dimensional thing and use that to figure out what the orientation should be on the lower dimensional thing. So as an example, in Stokes' theorem, the higher dimensional thing is the surface, and the lower dimensional thing is the boundary, which is some kind of curve. So in Stokes' theorem, you need to start by picking an orientation for the surface. Usually that'll be given to you in the problem. So the problem might say, the surface is a sphere oriented outwards. Now you know how to orient the sphere. That tells you that the normal vectors to the sphere should be pointed out of the sphere and not into the sphere. And now that you have those normal vectors, you can determine what the orientation has to be on the boundary. And there's two ways to do that. One of them is, like I said before, you can imagine standing on the boundary, facing the same way as the normal vector, and make sure that, and you need to go around the boundary in such a way that the surface always stays on your left. So as an example of that, we can imagine like a hemisphere that's chopped off at the top. So like I have, I think my screen sharing froze. You see the word test? Okay, I'm gonna try to reboot my screen sharing here. Hello, hi, sorry, I don't know exactly what happened there, but hopefully we're still all right here. Can everyone hear me and everything? You see my screen?
Yeah, we can hear.
Okay, great. Good. My computer just went a little wild. All right. So we're in a situation. We're trying to understand how to orient the boundary, knowing the orientation of the surface. So maybe we're in a problem. We have part of a hemisphere. So we chopped off a sphere around the equator, and then also a little bit higher up, we just have this like a little slice of a sphere. And let's say we're given that this surface here, which is this like the surface of this part of the sphere, let's say that surface is oriented outward. So we would interpret that as these normal vectors pointing out like this. And given that, there's two ways we can figure out how to orient the boundary. There's only one correct way to orient the boundary, and we can figure it out in many different ways. So one way to do it, this is the way I think the book does it, is to imagine we're at some point on the boundary. I'll just clear all these lines so we can see a little better. I'm at some point at the top of the boundary, and I want to know, should I walk, just to be clear, this point that I drew here is like towards me, towards the, or coming out of the screen, front of the figure. So I want to know, should I walk to the left or should I walk to the right? And what I need to do is imagine a normal vector pointing out from that point. So in our case, that would be something like this. And then I think to myself, I want to imagine myself as the normal vector. My feet are at the point, my head is at the tip of the normal vector. And I want to walk around the boundary in such a way that the surface stays on my left. So to do that, I have to walk to the left on the top here. And then go around the top like this. Otherwise, I would not be keeping the surface to my left. So that has to be the boundary orientation on the top. And on the bottom here, I need to walk to the right. Because here the normal vector still points the same way. But now if I were to walk to the left, I wouldn't be keeping the surface on my left. At the bottom, the normal vector wants to move to the right to keep the surface on its left. So that's one way to do it. This is like the keeping the surface on your left method, quote unquote. And it's a perfectly good method. So that's fine. Another way to do this is the like whirlpool method, where you imagine a point really close to the boundary. You imagine the normal vector there, and then you use the right hand rule. So you stick your thumb out in the direction the normal vector is pointing, and then I see which way my hand is curling, and I have to do this with my right hand. So I'm using my right hand, I'm pointing it in the direction of the normal vector out like this, and then I see my hands are curling like this. So the little whirlpool here should be in that direction. And now I notice that if I'm at the top of the boundary, these whirlpools are pushing me along to the left. On the other hand, at the bottom, the whirlpools are the same because the normal vectors are the same. But now, let me draw these whirlpools another way. These are the same whirlpools, just oriented upside down. At the bottom here, the whirlpools are pushing me to the right. So that's why the boundary orientation on this surface is different on the top and the bottom. On the bottom, the whirlpools are pushing me to the right. On the top, the whirlpools are pushing me to the left. Because on the bottom, I'm below the whirlpools, and on the top, I'm above the whirlpools. So that's the difference there. Does that help explain how to find the boundary orientation? And the same thing is true for the divergence theorem, although the divergence theorem I think is even easier. In the divergence theorem, the region itself, there's no kind of choice of orientation. The 3D region you're talking about, just a 3D region. You want to find the volume or integrate some function over there. But then the surface, the surface you get as the boundary of that region has to be oriented outwards. That's the rule for the divergence theorem. Okay. I think I had another request for a question, but I can't see it anymore because my chat rebooted. Something weird happened to my Zoom client. If you had asked another question, send it over again. Okay, so I have a request for problems from worksheet 10. Let me pull up that worksheet. If you want to see any of the previous worksheets, you can see my website, which I'll post another link to. That link in the chat will lead you to my website. It has all the worksheets, all that sort of stuff. Okay, so yeah, so someone asked, does the imagine yourself as a normal vector work every time? Yes, that works every time. It's completely the same as the whirlpool method, just in a disguised form. You just got to make sure to imagine. You just got to make sure to imagine yourself as the normal vector correctly, which sometimes I have trouble with. Like on this surface here, you have to imagine yourself standing on the surface with your head pointing out of the surface. So not that hard. But yeah, you can do it either way. You can use the right-hand rule to get those little whirlpools and figure out which way those whirlpools are pushing you, or you can keep the surface on your left, and those are both the same thing. Notably, I think it's probably good to make sure, if you looked at this like example we had, imagine that the surface instead was oriented inwards, so all the normal vectors are pointing in. Make sure you can convince yourself that if you tried to keep the surface on your left in that scenario, that the boundary orientations would both be backwards from what they are now. Good, like check for your understanding. So worksheet 10, problems 4 and 5 are the question. These are a little tricky. Also, I meant to update this PDF and I still haven't. Problem 4 should have an additional assumption. It's not that important, but just to be technically correct, in worksheet 10, number 4, we should also assume that F is not constant and S is bounded. This is just to make sure that like the stuff we're talking about even makes sense. But the idea for problem 4 is we want to know why the flux through S is non-zero, assuming that S is non-zero. The idea is that the gradient itself is going to be normal to the level surface. This is a concept we learned in 32A, I think, and it's a really useful one to know because it gives you a way to produce normal vectors to surfaces when you don't, without having to parameterize. So like you can start with a surface that's defined by some equation, and then you can figure out what is that the level surface of. You can take an appropriate gradient and find the normal vector kind of for free. It's a good thing to have in mind. And the reason that the gradient is normal to the level surface is that the gradient points in the direction of steepest descent. So if I were on my level surface, which remember the level surface is defined by the equation f of x, y, z equals 0. So everywhere on the level surface, the value of the function is 0. And the gradient at every point points in the direction to increase the value of f the fastest. So in fact, if I'm on the surface and my gradient were not normal to the surface, if my gradient were pointing, like in an extreme example, if my gradient were like tangent to the surface, that would make no sense because that means I could increase the value of the function by moving along the surface, which is impossible because the value of the function is always 0 on the whole surface. More precisely, if I'm on some part of the surface and I have my gradient here and it like isn't totally parallel, it isn't totally orthogonal, I mean, to the surface, I can imagine projecting that gradient vector down here. And this tells me if I'm not totally orthogonal, this projection down is going to be non-zero. And that projection down is telling me I can move in that direction a little bit and increase the value of the function. In other words, this is from the fact that the directional derivative, which maybe we denoted as, well, I'll just write it out. Directional derivative f in the direction of u is given by the gradient of f dot u, you might remember. But if I'm moving in the direction of the gradient, then the directional derivative, let's imagine here that I'm moving in the direction of this projection. So here's gradient of f, and here's the projection. So if I dot with the projection, then this quantity here tells me the amount that f changes when I move a little bit in the direction of that projection. And if that amount is non-zero, that wouldn't make any sense, because moving along the direction of that projection keeps me on the surface. It's tangent to the surface. I'm just moving along the surface in that direction. But on the surface, the value of f is always zero. So the amount that f changes as I move along the surface must be zero, because f is constant on the surface. And that means that this directional derivative has to be zero. But because that directional derivative is zero, it means that the projection has to be zero. And this is because the gradient is non-zero, and that uses the fact that f is not constant. So that's where this technical assumption comes in here. But knowing that f is not constant gives us that the gradient is non-zero, and because the gradient is non-zero, if gradient.projection equals zero, tells me that the projection has to be zero. And if the projection is zero, then that means that the gradient, that means that the gradient is normal to the surface. Because the only way to have my gradient vector be such that its projection is zero onto the surface is for the gradient vector to be sticking straight up out of the surface, to be totally normal to the surface, not point in any weird direction relative to the surface. So that's why I guess the moral of the story here is that gradient of f is normal to every level surface. Now, knowing that the gradient of f is normal to every level surface of f, could someone explain why in problem 4a on worksheet 10, why is problem 4a true? That the flux of the gradient of f through s has to be non-zero. Yeah, in answer to another question, I think the answers to worksheet 10 and the answers to worksheet 10 will definitely be posted in the next few days. Answers to the practice final, I'm not sure. Remember I think it might be good to think about, okay, we have this important fact that the gradient of f is normal to every level surface. Also in this problem, s is a level surface. So the gradient of f is going to be normal to s. And you should think about what happens when we try to compute the flux of the gradient of f through s. What is that integral? What integral do I write down for that? And then how do I actually compute that integral? Why is it important? Or why could it matter that the gradient of f is normal to s in that scenario? maybe try to break that problem up into small parts. If I was going to try to compute the flux of the gradient of f through s, what integral would I write down? The first question.
How are the pies, Ben?
Hello, they're going. Still killing apples.
You're adorable and we love you.
Thanks. Okay, so the first part of this question that we've broken into is just what is a flux integral? What does it mean to take the flux integral of the gradient of f through s? So is it the case, I don't know, maybe no one wants to answer? But I would appreciate if people would help me out here. If no one knows what a flux integral is, we can go over that. That seems important. Definitely is important. If we do know what a flux integral is, we should continue. So what would we do if we wanted to find a flux integral? What do I write down?
Are you asking for like the formula or like the visual like interpretation?
Yeah, just the formula. What would I write down if I wanted to find the flux integral of gradient of f through s?
Isn't it like the double integral like over the surface of like f dot d like s and like
that's
d,
right.
like the normal times like ds?
Right, and this, so this ds is like ds vector, where ds vector is the normal vector times the differential surface area. Exactly. And in our case, our vector field that we're trying to find the flux of is the gradient of f. So this is what I would write down if I wanted to compute the thing in problem 4, which says, which is talking about the flux of the gradient of f through s. This quantity that I wrote down here, that double integral, is the flux of the gradient of f through s. Okay, so now I want to know, using the fact from above that the gradient of f is normal to every level surface, and the fact that s is a level surface, I know that the gradient of f is normal to s in particular. So what does that help me do with this double integral that I wrote down? What does that tell me?
I might be wrong here, but does that mean it's 0?
So why do you think 0?
Because if it's normal to s, and then it's like the gradient times then okay, no, it's not 0. Never mind. I thought it through. I'm wrong. It's not 0.
It's not 0, but I think you're on the right track. So what are you thinking instead?
Okay, well, I'm thinking that like n is the normal vector to the surface. And so
it's the unit normal.
we just said that the gradient of f is also normal to the surface. So then is it just like the gradient of f squared?
Basically, yeah.
Because
So we remember we have to be a little bit careful, but that's basically the right idea. Is that if I take a vector and I dot it with itself, I get its magnitude squared. Which in this case, because we're looking at the normal vector, it's like this n that I wrote is a unit normal vector. So that magnitude squared would be 1. We have to be a little bit careful, which is for like maybe 2 reasons. First reason is that the gradient of f and n don't have to be actually exactly the same. All we know is that the gradient of f is a normal vector. It doesn't have to be pointed in the same direction as n. So like we could have n pointing this way and the gradient of f pointing this way. And those would both be normal to the surface, just like in opposite directions. Alternatively, the other thing that like is not makes gradient of f different from n is that gradient of f doesn't have to be a unit vector, whereas this n is always a unit vector. So at least in the way I wrote it here. So what we know at least though is that since gradient of f is not 0, we have that like gradient of f is some constant times n, which is where the constant is non-zero. That's just saying that gradient of f might be pointing in the same way as n, it might be longer, it might be shorter, it might be pointing in the opposite direction as n, but those are the only possibilities. It has to be pointing like in the same direction or the opposite direction, and it can't be 0. And then when I take this dot product of gradient of f dot n ds, what I have is some multiple of n dot n ds, and n was a normal unit vector, so that's this. And now, when I go to do that flux integral, what I end up with is lambda times the surface area. And lambda was not 0, and the surface area was not 0. That's not 0. So in other words, like more visually, what's happening here is that the flux, remember, is capturing how much is the vector field going through the surface. And in the scenario where we're looking at the flux of the gradient is normal. So the gradient is going through the surface always, everywhere, like by a good amount. It's going right through the surface. It's not going parallel to the surface at all. It's completely orthogonal to the surface. So the flux of that has to be non-zero. It is going through the surface. It's not passing along the surface in some other direction. That's the visual idea for that problem 4. And so knowing that, yeah. Sorry.
How do you know like when to use like the little n versus like the big N? Like for the normal.
It's a good question. I might have just used the wrong letter. Do you have maybe some examples from the textbook we could look at to compare? It's possible that the textbook always uses big N and I always use little n, and then those are just getting confused with each other.
No, the professor he's told us about both. I just don't know like when you use each. Like I've just been using big N and I haven't had a problem yet. So I don't know when you're supposed to use little n.
Let's take a look. Okay, so we have big N and we have little n. I see. Yeah. Okay, so the difference is big N is the vector we would compute. Usually the way we use big N only makes sense when you have a specific parameterization of the surface. So if you have a parameterization of the surface, we know how to find a normal vector by taking the derivative with respect to u, the derivative with respect to v, taking the cross product, and that cross product is the vector big N. But it depends on the parameterization you choose. If you choose a different parameterization, you might end up with a different vector big N, because you'll be taking the cross product of different things. So big N is a vector that like makes sense, but only relative to a given parameterization. And little n is really an intrinsic vector to the surface. It's a unit normal vector. So you can compute it from big N by taking the vector big N and making it a normal vector, just modding out by the norm, or sorry, dividing out the norm of the big N to get just a unit vector. But another way to think about it is if you have a surface, there's always like exactly 2 unit normal vectors at every point. Without knowing the parameterization at all, you don't need to know any parameterization. There's a normal vector like this that points out, and there's a normal vector that points in. And those are always your only 2 choices. And so there's always like one unit vector pointing out, one unit vector pointing in, or maybe there's not really an out and an in. At every point, there's always exactly 2 unit normal vectors. And so you have to choose an orientation first for your surface. But once you've chosen an orientation for your surface, then the little n refers to the unit normal vector that you chose in your orientation. So that doesn't depend on a parameterization at all. It just depends on the orientation of the surface. And you can start with a parameterization and compute little n in the way I said before. You take your parameterization, you find the big N, and then you make a unit vector. That's little n. But it's hard to go the other way because starting with just the unit vector, you don't really know how to parameterize the surface yet. So that's the difference between big N and little n. Is that little n is always a unit vector, and it doesn't depend on a parameterization at all. Big N might not be a unit vector. It could be much longer or much shorter, depending on what parameterization you use. And they're both useful. So the little n comes in handy when you want to think about the differential normal vector ds, like ds arrow, the vector version of ds. So that's the one that appears when we're taking flux integrals, that ds. And that ds is really defined to be this little n times ds not vector. So these two circle things are the same by definition. And the big N is also useful because big N, well, I guess another way to say it is maybe like something like big N, hard to exactly describe how to write this down without having more precise notation. But the idea here is that if I'm looking at part of a surface, I have a little differential surface area, ds, and I have a unit normal, little n. And alternatively, I could have like parameterized this surface. And so n ds is ds vec. And on the other hand, I could have some parameterization like g of uv, and then n hat is the partial with respect to u cross the partial with respect to v. And then this is like times du dv. And the useful thing to know is that n hat, all right, sorry. I think n is just this. And then the useful thing to know is that integrating something like, how does the book do it? Yeah, okay, this is a good way to say it. ds is the norm of n times du dv. If you have a parameterization, then this is true. The differential area ds is given by like a little change in u, a little change in v, but then times how much, or times like how fast your parameterization is traveling across the surface. And that's given to you by this normal vector here. If the big N is very long, that means that your parameterization is moving across the surface really fast. And if your big N is short, that means your parameterization is moving relatively slowly. So that's why this d capital S is multiple of du dv by how fast you're moving across the surface. It's like you can imagine parameterizing a surface half as fast, then I have to integrate over twice as big a region of u and v. And then my integral, like to find the surface area, I would integrate ds. Surface area is just the integral of ds over s. And this is the same as the integral over my bounds for u and v. I'll just write this vaguely as like integration over u and v. So this is saying when I want to compute the surface area, I should integrate over my bounds for u and v, and the quantity I should be integrating is like, how long is this normal vector? In other words, how fast am I moving along the surface? So if I move along the surface half as fast, I'm going to have to integrate over twice as large an area, and those two factors are going to cancel out to give me the same surface area. Does that make sense? It's like the difference between big N and little n. I think most importantly, big N is the thing you get from a parameterization, and little n is always a unit normal that doesn't have a parameterization.
So like, will they both give you the same answers, or will they give you different answers depending on which one you use?
Well, I think it only makes sense to use one of them. It usually only makes sense to use one instead of the other. So it does matter which one you use, because they're not really substitute. They usually very different. Big N, like if you have a problem where there's no parameterization given to you, you don't even have a way to find a vector big N. You'd have to make a parameterization first. That's one thing. And yeah, it does matter which one you use. In like, I guess similar to how if you were going to use little n, if you're going to use little n instead of big N, you like accidentally used little n, that would kind of be like doing u sub without doing a du. Like you just replace the like x squared with u, but you don't look for a factor of 2x. That would be bad. And that's basically the same thing as what would happen if you did little n instead of big N. They are just different things for that kind of reason. But the ways they appear, I think not too confusing. This one is when you have a parameterization, you can write ds, the differential area, in this way using big N. And if I don't have parameterization, then there's just nothing to think about with big N. There's no big N involved. I just have stuff like this. ds always exists, but if I have parameterization, I can describe ds in terms of magnitude of big N du dv. And then which one you use like depends on the situation. Like if I'm doing a flux integral, I have to be talking about little n. But if I need little n and I have big N, it's pretty easy to go between. This has to be the case because they're both normal, and little n is supposed to be a unit vector. Does that make sense? Like how to use the one you need?
Yeah, that makes sense.
Okay.
So it seems like I'm getting this right. Like if we have a parameterization, like I can just use like because I've been using big N because we've always had a parameterization. So like as long as we have a parameterization, we can use big N, correct?
Yeah, as long as you use big N correctly. So like if I had a parameterization and I was trying to compute a flux integral, I wanted to know like the flux of xyz dot ds, where S is like the sphere or something, then this is relevant to 4b, for example. What I would do is do x, y, z dot little n ds. But then I remember that this is the same if I have a parameterization as x, y, z dot little n times the magnitude of big N ds. Du dv. Okay, but then I remember that this thing is actually just big N. Because big N is just, it's in the same direction as little n, but it might not be a unit vector. It's scaled by its own magnitude. So this would be another way of writing the same integral, xyz dot big N du dv. But like, for example, it would not be right to say this is integral xyz dot big N ds. I think that doesn't even make sense. So it would make sense to say dot little n ds. This makes sense. And this one's no good. So is that helpful?
Yeah, it's helpful. Thank you.
Okay, great. Yeah. So yeah, it's like if you have a parameterization, then it's helpful to have this big N because it lets you write down what ds should be. But either way, ds always exists. Okay, so knowing that we have 4a, which told us that the flux of the gradient through a level surface has to be non-zero. how could we show that XYZ doesn't have a vector potential? That's 4b. My first hint would be, how can we use 4a to show that, well, one thing is, let's use the fact that XYZ does have a scalar potential. Let's find a function whose gradient is x comma y comma z. So I want a function f, so that gradient of f is x comma y comma z. What could I choose?
Couldn't you use 1/2 x squared plus 1/2 y squared plus 1/2 z squared?
Yeah, I think that's the best choice. There are many other choices, but that's the best one. Okay, this one's pretty easy to get because we want to know, okay, if I take the x derivative, I get x. If I take the y derivative, I get y. If I take the z derivative, I get z. I know functions that do that individually for each of those three variables, and they don't involve any of the other variables. I can just add them together. They won't interfere with each other. That's our function f. So that's good. The reason that's good is I want to use part A, right? And part A only tells me things about the flux of gradients. So in order to know something about this vector field, I should probably write it as the gradient of something. And so we've done that now. So part A now tells us that the flux of this vector field, x comma y comma z, through any level surface of this function f, well, in particular, the level surface x comma y comma z equals f of x comma y comma z equals 0, that vector field must have a non-zero flux through any of those surfaces. In this case, actually, I guess we should choose a different function because if you look at the level surface f equals 0, that level surface is just 1 point, and that does have 0 surface area. So that's maybe no good. Let's look at this one instead. I just add a constant on the end, and that doesn't affect the gradient at all. So now the level surface S is what? Remember, S is the level surface where f equals 0. What does that look like?
Is it a sphere?
Yeah, it's a sphere, because if I write down the equation 1/2 x squared plus 1/2 y squared plus 1/2 z squared equals minus 1 equals 0, I can move the 1 to the other side, multiply by 2, I get x squared plus y squared plus z squared equals 2. That should be a sphere of radius root 2. sphere centered at the origin, radius square root of 2. Okay. And now part A tells me that the flux of the gradient through that sphere has to be non-zero, right? So we know now that the integral of x comma y comma z ds is not 0. Why does this mean I don't have a vector? What does it mean to have a vector potential? What would I know if x comma y comma z has a vector potential? How can I write down what that means?
Isn't it like a vector potential when like a vector, like there's a vector field and like if you have like curl of like like if you take the curl of the vector field, you get like the different vector field and like
Yeah,
the vector
that's right.
potential is that different vector field.
Right. What it means for this vector field x comma y comma z to have a vector potential is that it's the curl of something. So if x comma y comma z had a vector potential, we would have x comma y comma z being the curl of some vector field. That's just the definition of vector potential. So if this were the case, what could I say about the flux integral I wrote above? What can I do with that flux? Just rewrite what it would mean. So if we had x comma y comma z equal the curl of f, then that flux integral would become this. And we know this is not 0. What else could I do to this integral?
This might be unrelated, but isn't that like how Stokes theorem starts? Or is that like
Yeah,
completely?
this is exactly the premise of Stokes' theorem. We look way back up here. That's the left-hand side of what I wrote for Stokes' theorem.
Is that
Stokes'
for a
theorem is
reason, or is
precisely
that,
the theorem. Sorry, what?
was that like for a reason, or is that completely unrelated?
No. That's very important here. The Stokes theorem just lets us evaluate integrals like this in a different way. Stokes theorem lets us evaluate the flux integral of the curl of a vector field as the integral over the boundary of the circulation. So if I were to use Stokes theorem here, what would this integral turn into?
Would it mean that the circulation of F is also not equal to 0?
Right, exactly. And the circulation of F over what curve?
Over the surface of the sphere?
Well, not the surface of the sphere, because that's not a curve, right?
Oh,
What does
over.
Stokes theorem tell me I should do the circulation over?
Isn't it the boundary of the sphere?
Yeah, right. Okay, and in this case, what is the boundary of the sphere?
Is it a circle?
It's not. In this case, the sphere has no boundary at all.
Oh,
It's a
right.
closed surface, and there's no like boundary curve on the outside. It's just completely closed up. And in that case, what does Stokes' theorem tell me that the right-hand side should be?
It should be 0.
Yeah, that's right. Which is, I think, maybe not obvious, but it is. That's the correct thing to do. If your boundary is empty, the integral over the boundary should be 0. So if you have no boundary at all, Stokes' theorem tells you that the integral over the surface of a curl has to be 0. But this makes no sense now, right? Because I knew that the integral of the surface of the flux of that curl had to be non-zero, but also it had to be 0, and those can't be true at the same time. So that's why it's impossible for x comma y comma z to have a vector potential. Because if it did, then I would be able to write the same integral in two different ways, where one of them is clearly 0 and one of them is clearly not 0. That's problem 4b. That makes sense as like or why that happened. Happy to run through that argument again at faster speed. That'll help. The idea was we wanted to show in part 4b that this vector field didn't have a vector potential, and we noticed that it is the gradient of something. So we found a function whose gradient it is, whose level surface at 0 had satisfied the hypotheses of part A. This function we started with, whose gradient was x comma y comma z, wasn't constant. The level surface was bounded. The level surface had positive surface area. We really had this like a really non-trivial level surface sphere. And the gradient of f was our function x comma y comma z. Part A told us that the flux of the gradient of f had to be non-zero. On the other hand, if x comma y comma z had a vector potential, the flux would have to be 0 by Stokes' theorem. So there's no way for both of those things to happen at the same time, and therefore x comma y comma z cannot have a vector potential. Might be a good question to ask. What's an easier way to show that the vector field x comma y comma z does not have a vector potential? And this worksheet was written before we had done the divergence theorem, but now we have more powerful tools. Now that we understand what divergence is, there's an easier way to show that x comma y comma z doesn't have a vector. How can I try to do that? That's a good thing to know, I think. I'll just explain. The one theorem we have now is that the divergence, so let me write it another way. Maybe I'll ask this question. What is the divergence of the curl of a vector field?
Isn't it 0?
Yeah, it has to be 0. And that's something that's not like, doesn't come from a theorem or anything. Well, if you like it, you could prove it with the divergence theorem. But more directly, you can just like write down what is the divergence of the curl of the vector field. You write down all the relevant derivatives, you add them all together, and they all cancel out and you get 0. This has to always happen. As a result, if I have a vector field whose divergence is not 0, it cannot have a vector potential. So let me write that another way. If the divergence of some vector field, let's say Q, is not 0, then Q cannot have a vector potential. Because if Q had a vector potential, then the divergence of Q would be the divergence of the curl of F, which is 0. So if the divergence of Q is not 0, Q cannot be the curl of anything. Also, very quickly, I'm going to have to grab my laptop charger, plug this in. So I'll be back in a minute. back. All right, so knowing this fact, how can we make sure that x comma y comma z doesn't have a vector potential? This idea here makes sense. It makes sense what I'm saying in that line. Just for the record, it is helpful to hear either yes or no. Those are both helpful things for me when I'm trying to explain this stuff. I'm not sure, should I explain again the equations I wrote on the tablet? Should I try to explain, or do those equations make perfect sense? And I should try to explain how those apply to the particular vector field x comma y comma z. Okay, so the equations make sense. And also, of course, they might make sense to some people and not to others. So if someone says they make sense and you're like, they don't make sense, also let me know. But assuming those look good, I want to use this to determine that x comma y comma z does not have a vector potential. Remember, what it means to have a vector potential is that you are the curl of something. A vector potential is a vector field whose curl is you. So if I want to show that x comma y comma z does not have a vector potential, that's just saying that x comma y comma z is not equal to the curl of any vector field. So I'm trying to show this thing here, that x comma y comma z does not have any vector potential. It cannot be equal to any curl. But then all I have to do is check this first condition over here. If I can show that the divergence of this vector field is non-zero, I will conclude that the vector field is not the curl of anything. That's what that line above means. So all I have to check is the divergence of xyz, which in this case happens to be 3, and that's not 0. So just simply plugging in the vector field we were talking about as the vector field in the statement gives us the result we wanted. This vector field x, y, z, its divergence is 3, which is not 0. And that means that the vector field itself is not the curl of anything. In other words, it does not have a vector. Does that make sense? Cool. So this technique of taking a vector field, taking its divergence, showing the divergence is not 0, and using that to conclude that the vector field does not have a vector potential. That's like a pretty that's going to be like a fundamental tool that we have. It could easily show up on the midterm. Even a question like problem 4 on worksheet 10 could show up on the final. I think that would be like a hard final question, but not not an impossible one to appear. But this technique of checking that a vector field does not have a vector potential by showing its divergence is non-zero is very important. It could definitely show up. It's exactly the same concept as like if you wanted to show a vector field doesn't have a scalar potential. Remember, a scalar potential for a vector field is a function whose gradient is that vector field. And we can check if a vector field has a scalar potential by taking its curl. If the curl is not 0, there cannot be a scalar potential because any conservative vector field has 0 curl. So this is really the same thing, just like at another level. To check for scalar potential, you take the curl, you make sure that's not equal to 0. In that case, if the curl is not 0, you can't have a scalar potential. And if your divergence is not 0, you can't have a vector potential. Basically the same test, and they just use like different theorems to conclude the fact. So like the curl fact comes from the thing that if I take the curl of the gradient of a function, I have to get 0. And the divergence comes from the fact that if I take the divergence of the curl of a vector field, I have to get 0. And therefore, if my curl is non-zero, then f can't be the gradient of something. And if my divergence is non-zero, then f can't be the curl of something. That's where these tests come from. But it is important to note that they don't go the other way around. So it's possible to have a vector field whose curl is 0, but is not conservative. And it's possible to have a vector field whose divergence is 0, but it doesn't have a scalar potential, or a vector potential. On the other hand, if your domains are simply connected, then the answers work both ways. So that's fine. All right, so and this appears on the worksheet of practice problems that's posted on the website as well. I think in problem problem 4 basically has this kind of thing occurring where you have a vector field whose divergence is 0, but it seems like the divergence theorem doesn't quite work, and the reason is because the divergence is 0, but there's no vector potential, and the vector field. Well, I'll leave it to you to work through that problem, but it's an interesting one. Problem 4 on the worksheet, the practice problem worksheet. Okay, but on worksheet 10, I was also asked to do number 5. So I think for this one, problem 5, part A. What did people have for their sketch of the surface S? If anyone sketched that out. My hands are going to be typing in a really comedic fashion. My camera's oriented in a weird way. I don't know. Any thoughts for how to try to sketch that kind of surface? Rho equals 1 plus sine phi. Let's look at this problem. Part A, sketch the surface S, which is the surface defined by rho equals sine phi plus 1. And use the restroom, so I'll be back in a bit. But give that a shot. See if you can produce some sketch of that. One hint is that the formula for defining the surface S doesn't depend on theta at all. So the surface should look completely rotationally symmetric. And you might want to think about, if you just take like one slice of the surface, what does that look like? Okay, I'll be back in a couple minutes. Okay, anyone have a sketch? Not that you have to share it on your camera, but just anyone have some reasonable idea? Or an unreasonable idea, that's fine too. Any thoughts are good. Maybe let's try an easier one. What would I sketch if the equation in polar coordinates was instead just rho equals 1? Not rho equals 1 plus sine phi, just rho equals 1. What is that surface? Yeah, that's right. It's a sphere of radius 1. Because remember, rho is the distance from the origin. So if I'm thinking about the equation rho equals 1, the set of points that satisfy that equation, the surface defined by that equation, is just the set of points whose distance from the origin is 1. And that's exactly what the sphere of radius 1 around the origin is. The unit sphere around the origin is just the set of points whose distance from the origin is 1. And that's, in other words, the set of points where rho equals 1. So if my equation was just rho equals 1, I would have a sphere. But it's not quite rho equals 1. We have 1 plus sine phi. So that's a little different. But what we know is that another way we can think about sketching rho equals 1 is we know it's going to be rotationally symmetric around the z-axis because this equation doesn't depend on theta. So if I just imagine my zx plane, let's say, and I'm not thinking about the y direction because once I draw like the zx plane cross section, I can just rotate that around and that has to be the right shape. If I were just to try to draw rho equals 1, I'm looking for the set of points whose distance to the origin is 1. So that's pretty easy to do. I get this cross section being a circle here, and then I rotate that around and I get a sphere. I tried to draw a circle, but it didn't work either time. I think I can have my tablet do this for me. All right, how's that? A little better. Still not great. Yeah. Aha. I think I can move it. Okay. All right, so that's some kind of circle. All right, so if I have this just rho equals 1, I would draw a circle, and I would rotate that around, and I would get a sphere. If I have this new equation, rho equals 1 plus sine phi, then what I'm describing is a surface where the distance from the points to the origin depends on phi. So in this picture, if I'm at a point here, phi is this angle, right? And I need to adjust how far out my point is from the origin by sine of phi. I need to add sine of phi onto there. So remember that phi can go from 0, where I'm pointing straight up, all the way down to pi at the very bottom, where I'm pointing straight down. So what is sine of phi going to be positive or negative or 0? Could be any of the above. What are the possibilities for sine phi in there? Yeah, positive is right. It has to be positive because if phi is between 0 and pi, sine phi is going to be positive just by looking at the graph of sine, for example. And what that tells me is that the points I draw in that cross section are going to be a little bit farther from the origin than 1, right? I'm going to be adding on a positive number to rho, so I should be looking for points that are a little farther than 1 from the origin. But not just like a constant little bit farther. The amount that they're farther away from the origin depends on phi. So the graph of sine I can think about looking like this. Here's 0, here's pi. And we can see that at the very top, when phi is 0, I'm not going to be adding any extra distance to the origin. And at the bottom, when phi is equal to pi, I'm not going to be adding any extra distance. But in between, I'm going to be getting farther and farther from the origin and then closer and closer again. So in this picture here, I should adjust my circle where at the start, I should still start at radius 1, adding 0. But then as I move out, instead of keeping the same distance to the origin, I'm going to increase my distance to the origin all the way up to pi over 2, and then I'm going to decrease it again. So it should look, I think, something like this. Kind of like a half of an apple. And the reason is that I start at a point here, and I'm going to increase phi a little bit, and my distance from the origin has to increase when I do that, because my function sine is getting positive. I'm adding stuff to 1. So because sine is positive as I go down here, I'm getting more and more distance added until eventually I'm going to shrink back down again, down to 1. So roughly like this, I think it should look. But I also know it looks pretty close to that because I plotted it. Let me show you the actual picture. Hopefully now you can see this 3D model of the surface. And it is kind of apple-shaped, right? That sort of thing. So if you were on a test and you had to sketch this, I think my sketching abilities are pretty poor. I don't know if I could really do a good depiction of this whole 3D thing, but you need to somehow communicate the following concepts. You need to show that you understand that it's going to be symmetric around the z-axis, and that each cross-section is going to be kind of like apple slice shaped. It's going to start at radius 1, and then it's going to get bigger outwards, and it's going to come back in, bulging like away from the center. If that makes sense. So any depiction you draw doesn't have to be perfect, but it does have to communicate this idea that there's like this dent in the top and the bottom, and that it's like it kind of looks like this. Okay. What if I were to modify this? Let's say I were to do, this might be a little tricky. Try a different one. Rho equals cosine phi plus 1. Any thoughts for what that's going to be like? I'm not going to press enter yet, but if I do press enter, we'll see a 3D model of the surface with cosine. Any guesses for what that's gonna appear to be? Or you can try to explain your thought process for how to try to visualize that surface. It's a good question. So will the object be rotated because cosine phi is the sine curve translated by pi over 2 units? Yeah, that's a good point. So if we consider the graphs of cosine and sine, okay, yeah, here are the graphs of cosine and sine you can see in the window there, and they're translated over from each other. So maybe an intuition would be the object is going to be rotated or translated or something like that. That's a good thought, but it's not quite right. Instead, what's happening here is, so remember in the sine case, if rho is just 1, we would just draw a sphere, but we had to modify how far out the points were by, like at the top, they stayed the same, then they had to be farther out than they normally were around, and they got back to the same point. And in the cosine case, we're going to want to do like a similar kind of thought. So remember, our phi can only go between 0 and pi. So our cosine curve, which is in, I believe that's orange on the screen, the curve for sine in blue told us that at the top, the radius should remain the same as if it was just 1. It'll be 1 plus 0. And in the middle, we're going to get 1 plus 1. So the radius at the very equator of that apple shape was 2. But in the cosine case, at the very top of the shape, when phi is 0 and we're facing straight up in the z direction, we're going to be adding 1 to our initial radius. So our initial radius was 1, and then we add on another 1. So at the very top of the shape, our radius is going to be 2. And then the extra radius that we're adding is just going to go down and down as we go down the shape, right? So let me plot 1 plus cosine. Here's a plot on screen of 1 plus cosine of x from 0 to pi. And this is rho, right? As phi goes from 0 to pi, rho is going to be 1 plus cosine phi for this adjusted surface. And so we're looking here at a plot of rho in terms of phi. The y-axis here is our value of rho. Our x-axis is our value of phi. This is telling us that when phi is 0 at the very top of the shape, the radius should be 2. And then as phi increases as I go down the shape, the radius should decrease. I should get closer and closer to the origin until all the way at the bottom, at phi equals pi, my value of rho should be 0. So that means at the very bottom of the shape, I'm at the origin. And then as I go up the shape, I move out to radius of 2 at the top. Radius of 2 at the top, radius of 0 at the bottom. So any idea for how that should look? At least that makes sense as to why it's maybe, even though cosine is translated over from sine, not that we're going to be rotating the surface, because we're not plotting like, how should I say that? Rotating the surface might happen if I added something to phi. If I added something to theta, maybe. Peach. That's a good idea. Yeah, I think it'll be something peachy. And yeah, if we were to try to like kind of sketch what this should look like in a cross section, I think I can peach with no crease. Yeah, I think that's right. So let's try it out. So this little divot here, this divot is at the bottom. And at the top, it's totally smooth. So it is kind of like an upside down peach, you might think. So the way we could have thought about that is, at the top, my radius is just decreasing. But then at the bottom, my radius is going to 0, but it's as I'm traveling down, I'm getting closer and closer to the origin. But even when I'm kind of close to the origin, my radius will still be positive. It's only at the very bottom that my radius is 0. So as soon as I move a little bit up from the bottom, my radius is positive, and that's why I have this pinch point at the bottom. I start at radius 0, but then my radius increases as I go out. And then at the top, it gets bigger and bigger, and I have the top of the peach. So does that make sense as a way to kind of visualize this surface? be able to make this translucent. Nice. Okay, it's a little bit translucent there if that helps. See the inside as well. Okay, right. So that's just some examples of how to try to plot some or sketch some surfaces in spherical coordinates. And 5b, let's try, which says use Stokes' theorem to compute the integral over the surface S f dot ds, where f, oh, I'm not sharing my iPad screen anymore, so you can't see that. Hold on. Here we go, okay. Back on the tablet, where f is the vector field, -4, -2x, -3y squared. Okay. So Stokes' theorem lets me compute certain kinds of surface integrals. It doesn't let me compute every surface integral. What are the surface integrals it lets me compute? So remember that, let me just write out the statement of Stokes' theorem. My tablet stopped screen sharing again. Try again. Stop. Okay, I'm going to switch back and forth. That's very annoying. Hold on. Okay. Ah. Incredibly laggy. Okay. Maybe we'll get there eventually. okay, so you can see my screen there where I wrote the statement of Stokes' theorem on the bottom. The integral over a surface S, the curl of f dot ds is equal to the circulation of f around the boundary of S. So the important thing to note is that this doesn't let us compute every surface integral ever. It only lets us compute the flux of a curl, right? On the left-hand side, that's the integral over S of a curl. We're taking the flux of that curl through the surface S. That's the only thing that Stokes' theorem lets me do. So in this problem 5b, where it asked me to use Stokes' theorem to compute the flux of this vector field F, my goal should probably be to realize the vector field F as the curl of something. The Stokes' theorem only lets me compute the integrals of curls. So I better know that F is the curl of something to use Stokes' theorem here. Or at the very least, I should get some curl involved somewhere so that I can try to use Stokes' theorem at all. Because Stokes' theorem only lets me compute the integrals of curls. So how can I try to figure out if F is the curl of something? I think this is something we discussed earlier. We have a way to check, at least, if vector fields have a vector potential. What was that way that we can try to check if a vector field has a vector potential? Right, yeah. So we check if the divergence equals 0. And if the divergence is not 0, then you can't have a vector potential. And if the divergence is 0, that may or may not give us enough information to tell if we have a vector potential. If our divergence is 0 and the vector field is defined everywhere, then we have a vector potential. In the same way that if we have a vector field whose curl is 0 and it's defined everywhere, then it's conservative. But just like in the curl case, if I have a vector field whose curl is 0, but the vector field is not defined everywhere, it's possible that the curl is 0 and it still doesn't have a scalar potential. It's not conservative, so that can happen. But for us, what we need to do is, I think my screen sharing is out of whack again. God, what's up with that? Okay, well, I guess I will try to explain this by sharing a window on my computer instead. So yeah, sorry, because my tablet screen isn't sharing correctly. Share my mathematical window instead. So now hopefully you see this window here, and let me set the font size much bigger. Okay. Size. Alt. Great. Okay. You can see this hopefully. -4 z cubed, comma, -2x. -2x, comma, -3y squared. All right, that's our vector field right here. And we want to check if the divergence is 0. So let's look at the divergence of that. I think we do that like this. Nope, that wasn't right. Hold on one moment. Div. There we go. Okay, see the divergence is 0. That's pretty easy to check because if we take the divergence of -4x, -4z cubed minus 2x and -3y squared, we're going to be taking the x derivative of the first component, the y derivative of the second component, the z derivative of the third component, and adding those results together. In this case, all of those partial derivatives are going to be 0, so the sum is 0. So this vector field has divergence 0, and the vector field is defined everywhere. There's no point where I can't compute -4z cubed, comma, -2x, comma, -3y squared. That always makes sense. So because this vector field is defined everywhere and its divergence is 0, it must have a vector potential. That means, what it means to have a vector potential, remember, is that it's the curl of something. So I know that this vector field f that I started with, -4z cubed, comma, -2x, comma, -3y squared, must be the curl of something. So I'm trying to find something whose curl is that vector field. Any ideas for how I could do that? How do I find a vector potential for this vector field? That's an interesting idea. Multiply the first part by x, the middle by y, and the last by z. And then, so then the hope there is that if we do that procedure and we take the curl to get back to the thing we started with, that doesn't quite work, but it's a good idea because you're thinking like, I'm going to take a derivative that'll like cancel out the factor of x, factor of y, factor of z. The issue is our curl isn't computed quite exactly in that way. When we do the curl of size here, we do the curl of some f sub x. Ugh, I don't know what these are. 1, f2, f3, respect to x, y, z. That didn't work. I'm not sure how to make Mathematica do this. Okay, but remember our curl is given by taking like partial with respect, the x component of the curl is given by partial with respect to y of the z component minus partial with respect to z of the y. So in other words, maybe I'll draw this and try to cast it again. If I want the curl of a vector field G to be my vector field F, what I need in the x component is that the partial with respect to y of C G. I'll put this down and I'll cast it in a sec. Ooh, that might be working better now. That's good. Okay. Hopefully you can see that on my tablet screen. If I wanted to have f, which is negative 4z cubed, comma negative 2x, comma negative 3y squared, be the curl of something, let's say that thing is g, then I need the following three equations that I wrote there. The first equation describes what would be in the x component of the curl of g. The second equation describes what would be in the y component of the curl of g, and etc. So we want to somehow find a vector field which satisfies all three of these equations. And like as a hint for the first one, it would be nice if I could have G3 be, it would be nice if I could just set it up so that partial of G3 with respect to y is 0, and partial of G2 with respect to z is 4z cubed, right? That would be an easy way to set it up. Can you see what I drew there? Is the tablet screen working now? Awesome, okay. So if I could get a vector field G, which is like G1, comma G2, comma G3, in such a way that partial G3, partial y is 0, and partial G2, partial z is 4z cubed, then the first equation would be true. That's helpful at least. And the reason I wanted to maybe have that particular setup is that 4z cubed is already the partial derivative with respect to z of something I understand very well. Like I know how to set this part up. I could just choose G2 equals z to the fourth, right? That would do it. So because that 4z cubed is familiar, it seems like the derivative of something with respect to z, it's the derivative of z to the fourth with respect to z. z. It'd be convenient if I could choose g in such a way that g2 is just z to the fourth, and partial g3 partial y is 0. That would be helpful. And so let's do something similar for the second equation. What would be a helpful thing to choose for g3 in the second equation? Nice, yeah. So in the second equation, if I could get partial g1 partial z to be 0 and partial g3 partial x to be 2x, then I'd be golden for the second equation. And this wouldn't contradict anything I've previously written either. So these so far seem all right. So what should I choose for g3 in order to make this happen? Yeah. Okay. And so far, this all seems consistent. It seems like I could do all these things at once and it would be fine. G2 should be z to the fourth. G3 should be x squared. And this, like setting g3 equals x squared, jives with my previous hope that partial g3 partial y would be 0. Those both make sense at the same time. So that's a reasonable choice to make. And also, I think this will help us out as well. Partial g1 partial z equals 0 is going to tell us something about what to do next. So in the next equation, in exactly the same way, it would be convenient if I could have partial g2 partial x equals 0 and partial g1 partial y be 3y squared. That would be nice. And in the same way, I know how to set this up. It'd be cool if I could have g1 be y cubed. And this works. If g1 is y cubed, then I think I've satisfied all my previous conditions as well. It's true in that case that partial g1 partial z will be 0. And the condition in the third equation that partial g2 partial x is 0 is also satisfied by my previous choice of g2. So making these choices that g1 is y cubed, g2 is z to the fourth, and g3 is x squared seems to be consistent with all the stuff I've written down. And indeed, if I were to just set that up, if I just had like g equals y cubed, z to the fourth, x squared, and I go and compute curl of g, I get exactly the vector field I started with. I get that. There. So what we've done here is really just like done an anti-curl by hand, which is possible in this case because it was just a particularly easy setup. And sometimes that'll be way, way harder to do. There is like a procedure, but it's very complicated. But just like how it's sometimes easy to integrate by eye, here we just anti-curled by eye. By I, I mean not by the letter I. Okay. So now that we know that f is the curl of something, the whole point was that I can use Stokes' theorem to compute the flux of curls. And problem 5b asked me to find the integral over s of f s, which we now know is the integral of the curl of g. So what does Stokes' theorem tell me I can do here? Right, exactly. Integral over the boundary of S, g dot dr. And it's been a little while since we did this, but remember that the surface S was that apple-shaped thing. So what is the boundary of that surface? Yes, the first part was where we sketched the surface, and the surface looked like an apple. So now in Stokes' theorem, we need to figure out what's, oh, sorry, should have put a boundary here. Now in Stokes' theorem, we need to figure out what's the boundary of that apple shape. What does that look like? Right, there's no boundary at all. So in the same way like a sphere has no boundary, it's totally closed up. It's the same thing with the apple. It's just a kind of a deformed sphere. There's no boundary curve at all. So what does Stokes' theorem tell me in the case that the boundary, there's no boundary? What does that mean? Right, the integral is 0 in that case. Okay, so that's the answer. It tells us that the integral of f dot ds is 0. And this problem took us a while because we had to go and like do this anti-curl in the middle. We had to find this vector field G whose curl was f, but secretly that wasn't actually necessary. On a final exam, all we'd have to do is make sure that the vector field f is defined everywhere. That's pretty easy. Check that the divergence is 0, and that tells us once it's defined everywhere and has 0 divergence, it must have a vector potential. And then we don't even have to find it, we just know it exists. Now we can jump straight down here and say, okay, it has a vector potential g. By Stokes' theorem, the integral has to be 0. That was those two problems. If there's any questions about those, happy to talk more about that, or we could do problems from the worksheet or from this like practice sheet of problems on my website or anything else. side note, I'm still working on this apple pie. I was a bit optimistic about how fast I could bake while also talking about math. But all the apples are sliced. I'm working on this sauce for the inside. I don't know what to call that. Glaze, I guess. So that's coming together. I wish I had like an overhead cam or something for that. We'll just have to make do. Okay. I think you can see. Yeah, okay. I have my phone as an additional camera. You can see me trying to put this pie together. Sauce is coming along nicely. Pretty nicely, a little lumpy. That'll be going inside the pie, making it a little bit caramelly, I think. I don't know, I'm just following a recipe from the internet. And I still gotta set up my pie crust. But over here we've got all the sliced apples and pie dish. I think I'll need 2 hands to actually do that. That's a little view of what's happening. Thanks. Yeah. I'll post a YouTube recording of this review session later. So I think at the end of this video, I'll take the pie out of the oven and take a look at that. But yeah, good luck studying. Thanks for coming through. I think I'll just stay around for probably another hour or so to let this pie bake. So if you have more questions, feel free to ask. Okay. I think everyone left is not actually from the class. So guess we're done with calc. But I'm just going to be here cooking. Okay. So I think the pie's done. And here it is. See, it's got a beautiful pie on it, the number, and otherwise looking pretty reasonable. Let's see a pie. So happy Pi Day and happy studying.